Thank you for joining me on this adventure. Your presence means the world to me. Welcome aboard as we set sail on a journey through FS Class E. The FS E is a class of Italian articulated electric locomotives. They were introduced in the course of the ERS until the ERS and have been decommissioned since 2006. They have been one of the most numerous Italian locomotive groups and have been widely employed during their long career, hauling every type of train, ranging from freight to long-range passenger services. Their introduction also saw the employment of some revolutionary for the time design concepts, such as the articulated carbody and the three bogies scheme. Now, let's shift our attention to history. The E was designed to overcome the problems shown in the ERS by both the E multipurpose and E high-speed locomotives, in order to better handle the increasing railway traffic in Italy. The E was the first Italian locomotive adopting the bo-bo-bo configuration with chassis divided into two articulated parts pivoting on the central bogie, which is very well suited for the often tortuous lines of Italy and that would have been later repeated on the E and E classes. The presence of a great number of wheels was considered important due to the presence of a number of high-slope lines in the Italian railroad network, as it increases the adhesion limit, meaning that the locomotive is less prone to wheel slips. The new engines weighted approximately 101 st. Engines were initially the same as E. The A used a 3 catenary, but this was soon shown to be inadequate and so were updated and provided with a new hollow axle transmission system. Mainly two different gear ratios were installed for sloping lines or heavy freight trains, maximum speed of 95, elevated later to 110, and the longer, with a maximum speed of 120, suited for passenger services. The locomotive was built in three different series: from 1940 to 1942, second series, from 1952 to 1956, third series, from 1957 to 1962. The first unit entered service in May 1940. 6 locomotives were destroyed during World War II. After the war, the total number of locomotives was brought to 469. Also thanks to the support from the Marshall Plan, and making it one of the most numerous groups of Italian locomotives. All the units were painted with an auburn livery. This was changed in the ERS to white one with green striped, the most trains XMPR livery. By ERS railway standards, these were old and uncomfortable. The original design of the cockpits proved absolutely unfit to modern safety standards. This was shown in an accident in 1996 at Sulmona, where the engine driver died despite the low speed, without being able to leave the cockpit in time. 200 units were therefore rebuilt and stripped of all asbestos. Starting from the ERS, these were used mainly for cargo services, save for the more backward Sicilian lines. Some units were lent to minor Italian railroads. The phasing out of the entire class was completed in May 2006. Now, let's shift our focus to technical details and embark on an intellectual exploration of its various dimensions. These are very simple locomotives. Most functions of the main command circuit are accomplished through various relays and contactors. In case of failure, the train driver could easily fix them to at least free the tracks. Also, especially in the last years of their service, these were the first locomotives that the new train drivers studied during their training courses, due to their simple working mechanics. In the following segment, we'll be examining motors and electrical description in greater detail. As most older Italian locomotives, it has a hostet formed by 16 cast iron resistors connected in series, for a total resistance of 29 ohms that needs to be gradually, but as soon as possible, excluded on start-ups, which regulates the current to the 6 at 200 DC traction motors, 2 per bogie. The motors can be connected in 3 combinations: series, series parallel and parallel. Each combination provides a progressively higher voltage to the motors, therefore increasing the current. Their setup is the following. combination motor setup voltage per motor series. All motors are connected in series 500V series parallel 2 branches of 3 motors 1000V parallel 3 branches of 2 motors 1500V. The rheostat connected in series to the traction motors is necessary because the DC motor has the intrinsic characteristic of absorbing a current inversely proportional to its rotating speed. At high speeds, it absorbs less current. This means that on start the current would be very high because the only resistance encountered would be only the one offered by motors and internal conductors, which is very low a short circuit in practice. The rheostat increases the overall resistance when starting the locomotive, lowering the current and allowing a smoother start. In SP and P combinations, the rheostat is divided in 3 branches connected in parallel. This lowers the overall rheostat equivalent resistance to about 3.5 ohm, while in South combination its elements are all connected in series. Like almost every Italian locomotive with rheostatic regulations, since each traction is controlled via a lever commonly referred to as manidion mounted on a support called roncola, this support has several notches, each representing a portion of the rheostat, plus 3 end combination notches and 2 transition positions, a bigger block between the notches. To accelerate, the driver rotates gradually counterclockwise the lever notch by notch, and in doing so the various rheostat contactors are closed, shunting the resistors and lowering the total rheostat resistance, also allowing more current to the motors. As speed builds up, the counter-electromotive force lowers this current until the rheostat is no longer necessary. It is, then, totally excluded, obviously if in traction and in an end combination notch. This safely allows traction for an indefinite period of time within certain limits. When the end combination notches are reached, the driver can then insert the single shunt one for each combination or make a transition to the next combination, reintroducing the rheostat, which has to be excluded again for the following combinations until the end of the parallel combination is reached. The shunts increase the current into the motors by shunting some motor spires through a contactor in parallel. This reduces the magnetic flux and, as said, increases the current since the two are inversely proportional. There are various shunt levels, depending on the locomotive, as is further explained. Usually, there is one per combination. It is also important to remove the shunts before making a transition, in order to avoid flashes due to abnormally high currents. Like some locomotives are not provided with the CEM motor combiner. CEM stands for Combinator Escluditor Motori, a device that, during transitions, rotates, combining the motors accordingly through various contactors. On this is achieved through the uses of more delicate spires, so transitions, especially backward ones, need to be very slow and gradual. The optimal moment to pass to the following pressing combination first-last notches is when the motor ammeter indicates 0 amperes, which happens when passing over the transition position with the lever. The driver should briefly stop in the middle of the block and pay attention to the ammeter, meaning that the motor contactors are in optimal position and is safe to proceed. Failure in doing this may result in flashes that will damage the contactors. An important parameter the driver has to consider, especially during rheostatic exclusion, is the current into the traction circuit. In particular, if he is excluding too fast, a wheel slippage can occur. In this case, the use of sanders and reducing throttle can help, and one or more maximum current relays can open when the maximum allowed current value is exceeded. The locomotive is protected from overly high currents through different kinds of relays: general maximum current relay MX, 3 motor branch maximum current relays MX 1, 2, MX 3, 4, MX 5, 6. REC is the electrical system used to provide the 3000 V coaches electrical heating maximum current relay MX REC. When they open, they also open the main breaker that cuts the connection to the catenary. Before the maximum currents for the relays were the following. Relay maximum current allowed MX 1050 MX 450 MX 350 MX 350 MX REC 500A. Between 1970 and 1980, The previous values changed. Relay maximum current allowed 1200 amps 450 amps 400 amps 400 amps EC 500A. As can be seen, the currents allowed in series are 450 A in both cases, while in series parallel and parallel combinations are 350 A and 450 A respectively. As said, one level of field shunt percentage of field weakening, 31% is allowed in each combination. However, some units received 90 to 250 used on FS Class E and at 200 type motors, which allowed a maximum of 5 levels of field shunt percentage of field weakening, 65%, 45% on the latters. These units were later made identical to standard ones again. Prepare yourself for an eye-opening discussion on motion transmission in the upcoming portion of this video. Units from 1 to 243 mounted Negri-type transmission, except for units 195, 198 and 176, 183 which had a rubber tampons in place of coil packs and double hollow axle transmission and rubber tampons respectively. All the following built units had the same transmission type of 176, 183 but slightly different. Different locomotives have received various gear ratios. See special units for more details. As we enter this new chapter, let's navigate the complexities of auxiliary and pneumatic services and unravel its multifaceted nature. The motor cooling fans were activated by two 4.53,000 V dedicated motors until Unit 201. Later units have one motors identical to the ones used on FS Class E. They are also used as dynamos to recharge the 24V batteries only if line voltage is greater than 1,500 V, used to feed low-tension devices, lights, locomotive heating systems, contactors, etc. Air production on the locomotive was granted by two type compressors. Later they were upgraded with the more reliable WAR. However, on some units, only one compressor was replaced, leaving one of each type in use on a single locomotive that produced air until 8 bar in main reservoir tanks were reached, while the WAR from 8 to. In fact, on these units, only the WAR was used on normal conditions, the other one only if pressure dropped below 7 bar. Main tanks and the 24V batteries supplies air and current to several systems. Braking system, which takes air from the main reservoir tanks and which is generally kept under a pressure of about 5 bar when brakes aren't unreleased. Main breaker, IR, which is the high voltage switch that connects the thread of the line to the locomotive. It can be closed only when pressure is greater than 5 bar. Contactors. They are widely employed on Italian electromechanic locomotives, including E. They are used in various systems, mainly to insets exclude the host's resistors, can move only when pressure is greater than 5 bar, and the IR must be closed. Horn and whistle, tromba and fiscio. The locomotives have 2 horns and whistles, one above each driving cab. The firsts are activated by a solenoid valve and work only when batteries are inserted and pressure is greater than 5 bar, while the seconds can reach their maximum frequency with pressures of about 4 bar. Sand throwers, sabbia. As the name suggests, they throw sand on the track in order to increase adherence. They are to be manually activated by the driver in case of wheel slip and work with pressure of about 5 bar. Flange oilers and gibello. During the ERS, in order to conserve the wheel flange, the locomotives have received a Delleman system that sprays oil via compressed air on regular selectable intervals into the channel between wheel flange and wheel surface of the front wheel. First pantograph raise compressor di primo alzamento. This small compressor, feed by the 24V provided by the batteries, is used when first activating the locomotive when main tanks are empty, to produce enough air to raise the pantograph for the first time. Originally the locomotive mounted a 7-position L-type Westinghouse brake controller and wheel-type locomotive brake, later replaced by the more common Orleconf and RM levers respectively. Brace yourself for an enlightening exploration of braking systems as we dive into its profound implications. The locomotive has three kinds of brake: hand brake, manually activated by two wheels in each cab, one for each bogie, which make the brake shoes clamp against the wheel. A total of 4 out of 6 axles are braked this way. Locomotive air brakes, freno diretto or moderable, takes air from the main reservoir tanks, bypassing the brake pipe and directly loading the brake cylinders of the locomotive, thus braking it. It is slightly faster than the continuous brake, but brakes the locomotive only. It is not advisable to be used to brake a full, wagon-fitted train, since it can cause a spring effect. Continuous, automatic air brake used to brake the entire train. It is a negative type brake and is called continuous because it extends itself through the entire train. Automatic because if brake continuity is no longer present. General pipe brakes, emergency braking is automatically applied. On units with braided type valves and Olicon levers, the brakes are gradual during braking and releasing. The working principles are the following. The braking system of the locomotive is formed by an array of components through a kind of tanks, called auxiliary reservoir, serbatio, oscillario, and command reservoir. 1 or 2 pipes, running along the train, called main pipe, not on every and generally only on passenger stock. Freight cars don't have it, and general pipe, the actual brake pipe. A tap, the controller which is used to graduate braking. A particular device called, which is divided into 2 chambers. One is kept at the general pipe pressure, which is variable, while the other at the command reservoir pressure, which is fixed to 5 bar, though may vary if the brakes are overloaded. In the middle there is a mobile piston. The brake cylinders. The brake rigging. When brakes are released, pressure in the brake pipe is about 5 bar and 0 bar in brake cylinders. To brake the train, the driver, by moving the brake controller, creates a depression in a particular tank called, which, through a series of coils, creates a connection to the exterior which makes the general pipe to gradually lower its pressure to a value equal to the one present in the aforementioned tank. How fast this happens depends on train length. The longer it is, the slower this procedure will be. Inside the command reservoir, pressure wins over now lower pipe pressure, and thus the piston moves, creating a connection between the braking cylinders and the auxiliary reservoir fed by the main tanks, which will then send a quantity of air to the brake cylinders proportional to the entity of the depression. The maximum pressure that can be reached into the brake cylinders on E is 3.8 bar, which corresponds to a pressure inside the general pipe of about 3.5 bar. In case of emergency braking, the brake pipe is put to direct communication with outside atmosphere, rapidly dropping pressure, and consequently making the train brake very fastly. Though there isn't a variation of braking power, only the braking speed is affected. To release brakes, the driver makes the pressure rise in via the brake controller. The pressure in the brake pipe is restored. Air is taken from the main reservoir tanks and from the main pipe if present to the value present in inside the brake pipe. Pressure wins over the command reservoir pressure, and so the connection between the brake cylinders and the auxiliary tanks is modified or cut, depending on the pipe pressure. The brake cylinders unload themselves, sending their air outside until their pressure reaches a value proportional to the entity of the depression. When pipe pressure is 5 bar, the cylinders will unload until they are empty. For a faster brakes release, it is also possible to briefly overload the braking system to a pressure proportional to the depression previously present, up to a maximum pressure of 7.2 bar. Shortly after this, the pressure drops to 5.5 bar and is gradually brought back to 5 bar in about 240 secs. However, on units with triple valves, distributor tipo, Westinghouse, and 7-position levers, braking circuit is slightly different. It is divided into parts like said before, but there isn't the command reservoir tank. When the pressure inside the brake pipe drops, it's directly the auxiliary reservoir that makes the frame put in the middle moving. Braking is not gradual on release. In this case, when the driver puts the controller on release position, brakes are fully released. If he brakes again too shortly after, there is the risk to have a loss of braking power because there may not be enough air to brake optimally, since the absence of the fixed pressure of the command reservoir doesn't ensure that there is enough air to safely release the brakes. It is even possible to fully exhaust the reservoir, with the consequent danger to not be able to stop the train at all. This is prevented in units with Breda and other types of valves, as the brakes cannot be fully released if there is not enough air in main reservoir tanks to brake again. There is a risk associated to the overload operation. Inside the pressures inside the two chambers are balanced. During the overload, both command reservoir and brake pipe pressures rise proportionally. As said, they are gradually lowered back to 5 bar, but it may happen that the command reservoir gets struck to higher pressure while the pipe pressure is lower. This keeps the connection between the auxiliary reservoir and the brake cylinders and consequently the brakes in effect. In this occurrence, a possible solution is to overload again the system so pressures can be rebalanced, or, if this doesn't work, to manually reset the command reservoir, emptying it by pulling a lever located outside. On units with 7 position levers, the risk is greater. The pipe is put to direct connection with the main tanks, and, if the controller is left for too much time in the overload position, it may reach a very high pressure, even 9 bar. It is very easy for the brakes to remain in effect in this case, and the only practicable solution is to manually empty the command reservoir tanks as said above. As we venture forward, let's take a closer look at mechanical modifications and its impact on our understanding. The locomotive is formed by 2 half carbodies pivoting over the central body. Between them, there is a bellows, which was originally made with rubber, then replaced in the ears by an impermeable membrane. In recent years, this was further replaced by flexible plastic material. On post-war units, 7mm reinforcement frames have been introduced on the chassis and under the cabs, as the first 108 units showed some mechanical weaknesses in those points. In the mid-ears, it was decided to reinforce only the chassis on pre-war units. However, units 26 and 65 never received these modifications. To reduce parasite motion, dampers were mounted between the carbodies, glycerine type from units 1-276 and special oil type from unit 277 onwards, although these were later eliminated in 1977 because considered useless. The first 108 units had different hosted ventilation shafts on the roof than the rest of the unit's ones, although these were later replaced with the more efficient shafts used on the latter units. They also had sliding oil buckles, while following units had rolling bearing ones. Units 160 to 171 were equipped with French-derived Adams buckles for testing purposes, which were later removed. Sand throwers were mounted internally into the body in the units 108. After the war, they were replaced by external ones that also were natively mounted on later units. In this section, we'll be deep diving into safety systems, unraveling its complexities and uncovering valuable insights. The first 108 locomotives originally had mounted a vigilance pedal designed by FS engineer Minichiani that required a periodic acknowledgement from the driver when the train was moving or emergency braking would have been commanded, but after the war, due to labor union pressures, it was discontinued. However, starting from the ears, many not all units received Rightation Signalia for Codice system, Hassler speedometer and a modified speed graph recorder Zona Tachographica that also recorded the codes received from the RS. As we enter this new chapter, let's navigate the complexities of special and experimental units and unravel its multifaceted nature. He was part of the PV train project and received photovoltaic cells used to recharge the 24V batteries. Due to this, it has been inserted in the R set of Italian historical units. It has been used for testing in 1965 of rheostatic braking. The same system was later adopted on FS Class E. A second, smaller lever was mounted on the top of the traction lever and was used to control the braking rheostat. This unit also mounted more and bigger vents on its sides. At this time, it has been stripped of many internal components and is not able to run. E is maybe the most famous unit of the group. The unit was involved in an accident where the driving cabin was damaged. FS decided to recover the unit and also decided to experiment a new type of driving cabin similar to the ones used on FS Class E. The unit is nicknamed Camilla, originating from which is supposed to be the girlfriend's name of a worker employed in the rebuilding works, who wrote it with chalk near one of the couplers of the locomotive. This unit is also historical. In 1951, units 44 and 89 received the 90 to 250 type motors used on FS Class E, and the gear ratio was also changed for a maximum speed allowed of 120 max power 2490 instead of 2100. The results of this experiment had proven successful, as these locomotives had the same performances as FS Class E gear ratio, but with less weight and power. However, they were later brought back to their original status. Units from 271 to 275 were built with different bogies than the standard ones, similar to the ones used on the FS Class E prototypes. 200 motors, 5 shunt levels, and a gear ratio of max speed 105. These units were later made identical to standard units. During the Unsoldo Breda built a locomotive derived from E for use in Yugoslavia, classified 362. I'm here to provide you with the best information, so let me know what else you'd like to learn about.